Well, in fact, we also have determined what the isolated points here are. Well, none of the points in here, they're isolated points. An isolated point must belong to the set anyway. But here, all of these points, as we have seen, no matter how close to each other they come, they will have a positive distance from the closest point in the set. So they will be isolated points. Isolated points of A. They're 1 minus n minus 1, 0. But here we have to be a bit careful. If n is 1, then this becomes 0, 0. But 0, 0 is not an isolated point. So everything else from here on, that is, we'll write n is in n with n larger than or equal to 2. Now, we decided to refer to the totality of cluster points and isolated points, that is limit points, as the closure. This will then be xy in R2 such that we have this set x squared plus y squared less than or equal to 1, x larger than or equal to 0. In fact, 0, 0 is in here as well, because 0 is less than or equal to 1 and 0 is larger than or equal to 0. Union 1 and minus 1, 0. Here, I can just take n equals 1 as well. 0, 0 will belong to both of these sets, but never mind. But we'll have minus 1, 0 as well. Finally, boundary points. Now, everything on here, on the circle, that will be boundary point, because no matter what epsilon ball I take, it will have both a non-empty intersection with both the set and its complement. Points on here, they will also be boundary points, because no matter what epsilon ball I take, it will satisfy the condition of a boundary point. What about these isolated points? Are they boundary points? Well, no matter what epsilon ball I take about this, will it contain points from cap A? Yes, the center will belong to cap A, but it will contain also points outside. Here, these points, they do not belong to the set. They belong to R2 minus A. Is this point a boundary point? Well, no matter what epsilon ball about this I take, it will contain points of the form 1 over n minus 1, 0 for n large enough. But the center itself, that's outside the set, it contains points from outside the set as well. So this will be del A xy in R2. Now I need to formulate the points on the circle. So they will be x squared plus y squared equal to 1 now. But x larger than or equal to 0. Then I need to include this portion, which I can write as 0 crossed with the Cartesian product of the singleton 0 with the interval from minus 1 to plus 1 in the second component. Union, I have 1 over n minus 1, 0, n in n, They all belong, and union -1, 0. Here, let me ask the following question. These isolated points, they turned out to be boundary points as well. Do you think that will be in general so in any metric space? Now we said these are isolated points, but if I take any open ball about them, any epsilon ball, that will contain points from the set cap A because the center belongs, and it also contains points from outside. Do you think that will be in general true? Will any isolated point be a boundary point in a metric space in general? Yes. It will not, but let's wait the coming examples. So this is peculiar to a Euclidean space, to the usual metric. Next, let's again take R together with the usual metric. But this time, let us take as our set A the set of rational numbers. Now, let's consider first the interior points. Well, an interior point of Q, that must belong to Q. A cluster point, a limit point, a boundary point, well, they need not be members of Q, but interior points and isolated points, they are by definition members of the set. So take any x in Q. Is that an interior point? Well, the question is whether we can find some positive epsilon such that the epsilon ball about this, which is just the interval from x minus epsilon to x plus epsilon, that will be contained entirely in the set of rationals. Take any epsilon positive, but consider x minus epsilon, x plus epsilon. Do we know anything about the structure of Q to decide whether this is entirely contained in Q or not? Now we know the following. If A is less than B, two real numbers, then the interval from A to B, excluding A and B, that contains both rational numbers and irrational numbers. Intersection R minus Q is non-empty. That is, x minus epsilon, x plus epsilon, this is not contained in Q. What is our conclusion about x? Is it an interior point? No. No matter what epsilon we take, the epsilon ball about that point, the interval from x minus epsilon to x plus epsilon, that contains points from outside Q, so it's not contained in Q. Thus, x is not an interior point of Q. So, what do we know about Q interior? It's empty. Now, take any x in R. Can that be a cluster point? Is that a cluster point of Q? Well, let epsilon be positive. Now we'll consider the epsilon ball about x, but we'll take x out. Now, BD epsilon of x minus singleton x, but this is nothing but x minus epsilon x union x plus epsilon. The question is whether this, for any positive real number epsilon, has a non-empty intersection with Q. But we know between x minus epsilon and x, for example, there are rational numbers here as well. So this intersection Q, this intersection Q is non-empty. So no matter whether x itself is rational or not, it's a cluster point. Okay? Any x in R is a cluster point of Q. But we know, being a cluster point and being an isolated point, they're mutually exclusive. If something is a cluster point, then it cannot be an isolated point. But we can also see that this has no isolated points at all directly. Well, if x is in Q, no matter what epsilon I take, x minus epsilon plus x plus epsilon intersection Q, that will contain rationals other than x. X minus epsilon less than x, there will be rationals in between them, and they will be different than x. So, no isolated points. But what can we tell about Q closure? Well, these are all limit points since they're cluster points. So this is R. What about boundary points? Well, actually we have information about that. Well, for any x in R and any epsilon positive, x minus epsilon, x plus epsilon, intersection Q, that's non-empty. This contains rationals, but x minus epsilon, x plus epsilon, this is just the epsilon ball about x with respect to the usual metric, R minus Q, the intersection, that will be non-empty as well. So every point in R is a boundary point of Q. So every x in R is a boundary point of Q. So del Q, that's R. So here we have two extremes. The interior, that's empty. The closure, that's R. Boundary, that's R as well. Now, as our last example here, let us turn to the two extremes in terms of topologies. Given a non-empty set, we have the indiscrete topology and we have the discrete topology. The indiscrete topology, consisting of the empty set and the entire space, that's the coarsest topology. Well, the other declares every subset as open. That's the finest topology. Let's see how things work there. But for that, let's assume that the underlying set actually contains at least 2 points, because if it's 1 point set, then that's the trivial case. So example 3, let X be a set with X having at least 2 members. Now let's take first tau 1, which is this topology. Now let's assume that A is non-empty. It will be in X, but it's different than X as well. Neither the empty set nor the entire space. Well, you might say, well, but that will depend what happens here. That will depend upon what cap A is. Well, X could be anything. X can, for example, be Rn as well, or the set of all real-valued functions on 0, 1, and so on. Well, the subsets, they're very rich, but we'll see that actually this topology is such that no matter what this set in particular is, we can determine its interior, its closure, and its boundary. Let's start with the interior. Take X in A. If you check this for being interior or not, well, X should be in A if it's an interior point. If it's outside A, it's not an interior point. Okay. Is it possible that A is a neighborhood of X? Well, A being a neighborhood of X, that means there is some open set G which contains X and which is contained in A. But what are the open sets in this topology which contain X? Just one. It's cap X. But cap X is not contained in A because A was taken a proper subset of this. Okay? Now, as the only set, the only open set with the only open set G with X in G is X, and X is not contained in A. X is not an interior point. Of A. So, A interior is empty. Well, if we had taken the entire set cap X, its interior would be equal to itself, everything. But so long as one point is missing, it's a proper subset, it has an empty interior. Okay? Let's check for cluster points. Take X in X. Now let's check whether this is a limit point or not. Let's take a shortcut. What should be the test this point has to pass in order to be a limit point? Well, we'll take any neighborhood U. We take the intersection of that with the set A, cap A. If that's non-empty for any neighborhood U, well, then this will be a limit point. So let U be any neighborhood of X. But can we tell about what U then will be? Well, that will be the entire space, because there should be some open set which contains X and which is contained in U. But the only open set which contains X is cap X. If that's contained in U, U must be cap X. Then U is equal to cap X. So this has a unique neighborhood, but U intersection X, that will be, I'm sorry, not U intersection A, that's X intersection A, that's non-empty. So no matter what X you start with, that will be a limit point. Thus, A closure was the set of all limit points of A. It's the entire space. What about the boundary? Take any X in X. Let U be any neighborhood of X. But then, as above, U is equal to X. So, U intersection A, that's non-empty. U intersection X minus A, that's X minus A, because U is X. But we have taken A to be a proper subset of cap X, so X minus A is non-empty as well. So, the boundary, that's the entire space. What would the boundary of cap X be? Well, if you consider the entire set, no matter what topological space you consider, this boundary will be empty because its complement will be empty, and any neighborhood with the complement will have an empty intersection. Okay, so that's A. Now let's pass to the other extreme. Here, everything is open. Here we will also discover why we refer to this topology and to the corresponding metric as discrete. When would you call a set X discrete? If you go through all the attributes of points pertaining the relationship a set is, well, if every point is isolated, then pictorially that would match, that would fit being described as being discrete. Now here we'll see, no matter what set A we take, now let us again take A as an intermediate set. We'll see that every point in cap A will be an isolated point. Now first, X in A. Will that be an interior point? Will there exist a neighborhood of X which is entirely contained in cap A? What would that be? Singleton X. Now, singleton X, that's in tau 2, and X is in singleton X, that's contained in singleton X. So X is a neighborhood of X with X in A. So X is an interior point of cap A. Thus, A interior is just A. What about A closure? But let's check now for each X in A. Also note that the set A intersection singleton X, which is a neighborhood of X, is equal to X. So every X in A is an isolated point of A. And as I said, this is why we refer to this topology as the discrete topology. What about cluster points? Take any X in A. Any X in, cap X. Because to be a cluster point, it need not be a member of the set itself. It could come from outside. Will that be a cluster point? No. Again, singleton X is a neighborhood of X. So this is a neighborhood of X. This intersection A, that will be empty. And this, no matter whether it comes from cap A or from outside. In fact, this tells us that no X in A is a cluster point. We have noted if you take the set A and a point from that set, it cannot be simultaneously an isolated point and a cluster point. No cluster points. So what's A closure? That's A again, because everything is an isolated point, so everything is a limit point. But from outside, there are no cluster points, so there are no limit points. Now, here, the interior was empty. The closure was the entire set, so they were stretched to the opposite extremes. But here, both the interior and closure, they're just equal to the set itself. They're being attracted by the set A. What about boundary? Now we can answer that easily now. Take any X, be it from cap A or from outside. Singleton X is a neighborhood of that. Now, if X is in cap A, singleton X will have an empty intersection with the complement. If it's from the complement, singleton X will have an empty intersection with the set A. Now, when X is in A, singleton X is a neighborhood of X with singleton X intersection X minus A is empty when X is from outside A. Well, singleton X, again, a neighborhood of this, but this time X intersection A will be empty. So it has no boundary points. Thus, del A, that will be empty. So you might have isolated points which are not boundary points. So I guess this list of examples, well, gives us enough idea what can happen to the points in terms of their relationship to a given set. Now, let us see to what extent this structure introduced will simplify life. Now, well, the starting point, the point of departure in a topological space, well, that's the open sets, could be the closed sets as well. Once the open sets are given, we know what the closed sets are. The complement should be open. Or when the collection of all closed sets is given, we know what's open. So, well, then the first thing is, can we find new characterizations of openness or closedness of a set, well, in such a way that will make life easier for us. Now, let's start with open sets. Now let X tau be a topological space and A a subset of that. Now the following are equivalent. One, A is open. Two, A is, well, okay, every point of A is an interior point of A. Thirdly, A is a neighborhood of each of its points. Now, these are to show the equivalence of three statements. Now, the simplest way is to follow a triangle. Show that 1 implies 2, 2 implies 3, and 3 implies 1. Then you will have established equivalence between any two of them. So we'll follow that. But some of the implications here, they're obvious. 1 implies 2. So assume that A is open. Take any point of A. What's the definition of an interior point? Whether A is a neighborhood or not. But an open set containing a point, that's a neighborhood. Since if A is open, A is a neighborhood of each of its points, so each point is an interior point. Well, if every A is an interior point of A, well, by definition of an interior point, 3 must hold. A will be a neighborhood of each of its points. So 1 implies 2, 2 implies 3. They're obvious. But let's check whether 3 implies 1 as well. Assume that A is a neighborhood of each of its points. We'll show that A is open. Well, assume that X is in A. What does it mean that A is a neighborhood of X? By definition of a neighborhood, there should exist some open set G which contains X and is contained in A. Okay? Well, let me denote that, well, there might be many such open sets, but let me pick one and use the notation of G sub X if it is an open set containing X and is contained in A. Now there is some open set G sub X, well, that is G sub X is in tau, with X in G sub X, and that's contained in A. Okay? Now, what if I take the union of all such G sub X's? Will this set be open? Yes, it's the union of open sets, a non-empty collection of open sets. So this is open. But how is that related to A? Each G sub X is contained in A, so this union is contained in A. Now, if I take conversely any point y from cap A, will that be in this union? Yes, there will be G sub y which contains that. So we have this. This union will be cap A, but moreover, it will be open, so A is open. Next, we'll have a characterization of closed sets as well. Proposition let X tau be a topological space and a subset of X. Now A is closed if and only if A contains all its limit points. So limit points were points which are arbitrarily close to the set. So closedness and containing everything which is arbitrarily close to itself, they're equivalent. Let's go through the proof of this as well. Assume that A is closed. Now, let me take any limit point X of cap A. Now I will be careful here. Well, cap A might be such that it has no limit points at all if it's the empty set. If it's not the empty set, it will have limit points, because no matter every point of the set itself, that's a limit point. But in order not to distinguish whether A is empty or not, instead of saying take any limit point x of A, which requires the existence of limit points, assume that x is a limit point of A. If we show that this then belongs to cap A, we'll be done. Okay? Suppose x is not in A. That is, x is in x minus A. What do we know about x minus A? It's open. So if x belongs to cap x minus A and x minus A is open, x minus A is a neighborhood. But it has an empty intersection with A, contradicting that x was a limit point of A. Now, x minus A is open, thus a neighborhood of x with x minus A intersection A being empty, contradicting that x was a limit point. Because we have shown x is a limit point of A if and only if for every neighborhood U of A, U intersection A is non-empty. Here, we have exhibited some neighborhood of x which has an empty intersection with the set A in contradiction with this. Now, let's see the converse as well. Conversely, assume that A contains all its limit points. We need to show that then A is closed. But by definition, A will be closed if x minus A is open. So if we show x minus A is open, that'll complete the proof. Now, assume that x is in x minus A. By this hypothesis, what do we know about x? It's not a limit point of A, because A contains all its limit points. If something is outside A, that's not a limit point of A. Then x is not a limit point of A. But what happens in that case? By definition or by the characterization of a limit point, there must exist some neighborhood U of x which has an empty intersection with A. So there is some neighborhood U of x with U intersection A is empty. But then how is U related to x minus A? It's a subset of x minus A. Then U is a subset of x minus a. But x minus a, being the superset of a neighborhood of x, is a neighborhood of x itself. U was a neighborhood of x. X minus a contains that. So x minus a is a neighborhood of x. But x was an arbitrary member of this. We have shown that x minus a is a neighborhood of each of its points, which means x minus a is open via this proposition. So x minus a is a neighborhood of each of its points. Hence, x minus a is open by the above proposition. Implying that see, A is closed. Completing the proof. Okay, I guess we can stop at this point. Now we'll continue with further tools which this classification of attributes pertaining to points equip us next time. And then we'll turn back to metric spaces again, and we'll see that some tool which is familiar to you from high school on turns out to be very useful in characterizing topological properties of metric spaces. That will be the notion of a sequence. Sequences will be useful, very useful, but for R and Rn, not in general metric spaces to some extent.